Hey everyone, and welcome to this explainer. Okay, today we are embarking on a seriously fascinating journey. Think about it. Every single day, you use this incredibly complex biological machine to communicate your thoughts, your emotions, basically your very identity to the whole world. And you do it completely effortlessly, probably without a second thought. But the literal mechanics happening inside your mouth, throat, and chest to produce even a simple greeting, it is staggering. So today, we are going to decode the actual code of human speech, reverse engineering the voice to understand exactly how we do what we do.
So here's the big question I want you to keep in the back of your mind as we go through this. How exactly do we teach a piece of silicon, a computer, to understand the spoken word? On the surface, it sounds like a straightforward computer science problem, right? But the brilliant truth is that to teach machines to hear and speak, scientists first had to look in the mirror. They had to reverse engineer our own physical anatomy and biological algorithms. To build the speech recognition and text-to-speech software we use every day, we first had to completely digitize the human voice.
Okay, let's dive right into our roadmap for this explainer. We'll start with the code of human speech, then move on to our acoustic hardware and sculpting consonants. After that, we'll hit shaping vowels and syllables, the rules of assembly, and finally, the music of prosody. Let's jump right into Section 1, the code of human speech.
You know humanity's obsession with breaking down speech? It's actually ancient, like really ancient. We can trace this all the way back to 3000 BC. The earliest writing systems, like Sumerian, started out as logograms, where one symbol meant a whole word. But eventually they evolved so that a single symbol could represent just a phonetic sound, like the syllable ba. Fast forward a few thousand years to 1888, and linguists created the International Phonetic Alphabet, or IPA, to standardize all of this. And by 1980, as the computer age really dawned, we needed something machines could easily read, leading to the arbabet. What this history shows us is an implicit, enduring idea. The spoken word is not just a continuous, messy noise. It's actually composed of smaller, computable, distinct units of speech. So the absolutely crucial point here is that if we actually want a computer to process speech, we can't just rely on our standard alphabets. A regular letter is just, well, it's way too opaque. Think about the English letter C. In the word cougar, it sounds like a K, but in the word cell, it sounds like an S. If you feed that inconsistency to a computer, it's going to get very confused very fast. Instead, we use what's called a phone. A phone is an exact, abstract representation of a specific speech sound. It's essentially the purest unit of pronunciation.
And this brilliantly illustrates exactly how computer scientists solved that massive transcription problem. Instead of using those complex phonetic symbols that early computers just couldn't process, they mapped these pure phones using simple ASCII characters. The sh sound in squash becomes, well, ch. The ch in cherry becomes cha. They systematically turned the fluid, messy reality of spoken English into a highly structured, readable database that could actually be fed into a machine. They essentially created the source code for English pronunciation. But, as we know, code is just software. To really understand speech, we have to look at the machinery running that software.
Which brings us to Section 2, our acoustic hardware.
All right, so these are your vocal organs. This is your built-in biological acoustic hardware, and honestly, it is a total marvel of engineering. It all starts down at the bottom. The lungs expel air up through the windpipe, technically known as the trachea. As that air rushes up, it hits the larynx, your voice box. From there, the air has to escape the body, and it does that by traveling through the vocal tract, which branches into either the oral tract, meaning out the mouth, or the nasal tract, out the nose. Every single sound you make relies on modifying this flow of air as it travels from your lungs out into the world.
Right there in that larynx, we have our very first major sound modifier, the vocal folds. They give us the critical distinction between voiced and unvoiced sounds. And I want you to actively participate here with me. Gently place your hand on your throat, right over your Adam's apple. Now, make a continuous Z sound, like a buzzing bee. Zzz. You feel that strong vibration? That means your vocal folds are pulled close together, vibrating like crazy as air passes through. That's a voiced sound. Now, switch to an S sound, like a snake. S. The vibration completely stops, right? For unvoiced sounds, your vocal folds pull far apart, letting the air rush through without vibrating at all. It's a simple physical switch, but it fundamentally changes the output of our hardware. Okay, so now that we have air flowing, how do we shape it into specific letters?
Let's get into Section 3, sculpting consonants.
So, consonants are entirely defined by actively restricting or completely blocking this airflow we just talked about. And linguists have a literal map of exactly where we create these restrictions. They call this the place of articulation.
We can block air right at the front using our two lips for bilabial sounds, like the P in possum. We can move a bit further back to the teeth for dental sounds. Further back still is the alveolar ridge, that hard little bump just behind your upper teeth. Then there's the palate, the roof of the mouth, the velum, the soft flap way in the back, and finally all the way down at the glottis in the throat. Your tongue is incredibly agile, darting to all these different locations in fractions of a second to sculpt the air into consonants.
Now, I want you to pay close attention to your own tongue for just a second. Seriously, try saying the word thing. Notice how the tip of your tongue pushes slightly between your teeth? That's a dental sound. Now, say the word soup. Your tongue pulled back, didn't it? It pressed up against that hard alveolar ridge behind your teeth to make the s sound. We are talking about just millimeters of difference in the physical placement of your tongue, but it completely rewrites the acoustic signature of the air leaving your mouth.
But, it's not just where we block the air, it's how we block it. Linguists call this the manner of articulation. Sometimes we completely cut off the air and let it explode out. These are stops or plosives, like a P or a T. Sometimes we block the mouth entirely and force the air out the nose. Those are nasals, like M or N. Then we have fricatives, where we force air through a tiny little gap to create a turbulent hiss, like an F or an S. We also have affricates, which basically combine a stop and a fricative, like the ch in chicken. And of course, we have approximants and quick flaps. Our biological hardware utilizes all these different mechanical techniques to give us this incredibly rich, diverse library of consonant sounds. So consonants are all about blocking, cutting off, and restricting air. But what happens when we let the air flow freely?
That brings us to Section 4, Shaping Vowels and Syllables.
Unlike consonants, vowels have way less obstruction. They are the loud, long-lasting, open-air sounds of our language. And notice how your tongue position changes for these. Say the word beat. You'll actually feel the highest part of your tongue push forward and up towards the roof of your mouth. Now say boot. You should feel the bulk of your tongue physically slide backward. And if you say bat, your tongue drops much lower. By adjusting the height of the tongue, the frontness or backness of the tongue, and whether our lips are rounded or flat, we basically tune the open cavity of our mouth like a biological synthesizer to produce different vowel frequencies.
Linguists actually map all of this out on a chart called the vowel space. It might look like a simple triangle, or, well, a trapezoid really, but it's actually a biological coordinate system. The vertical axis represents how high the tongue is in the mouth, and the horizontal axis represents how far front or back it is. Every single dot on this graph is a specific vowel phone. Some vowels are just single points, while others, like the sound A or ow, are actually paths, meaning the tongue actively moves through the space while making the sound. This is called a diphthong. It's literally a map of human tongue movement.
Moving right along to Section 5, the rules of assembly.
So now that we have our basic hardware outputs, we need the software rules to stitch them all together. We combine consonants and vowels to build syllables. A syllable always has a core, which is almost always a loud, sonorant vowel sound. We call this the nucleus. Let's assemble the word dog. The core vowel, the ah sound, is our nucleus. Then we can attach initial consonants to the front of it, which we call the onset. In this case, the d sound is our onset. Finally, we can add ending consonants after the vowel, known as the coda. The g sound acts as our coda. Fun fact, the nucleus and the coda together are actually referred to as the rhyme. Step by step, this is exactly how our brains package individual phonemes into usable chunks of speech.
But wait, you can't just throw any random sounds together. Every single language has strict software constraints on which phones can legally follow each other. This rulebook is called phonotactics. Think of phonotactics as the bug-checking system of a language. For example, in English, our phonotactics simply do not allow a syllable to start with the sequence ZDR. It completely violates our internal rules. Other languages might allow it, sure, but for an English speaker, the hardware will practically refuse to process it as a natural start to a word. And this underlying logic is exactly what we have to program into computers so they know what words are actually statistically probable.
And finally, we arrive at Section 6, the music of prosody. Okay, we have our sounds and we have our syllables. But think about it. If you just read syllables out loud with zero variation, you'd sound exactly like a 1980s robot. To sound human, we need one final layer. Prosody is the overarching melody, rhythm, and intonation that we drape over our syllables. It involves dynamically varying our pitch, our volume, and our speed. And it dictates discourse structure. I mean, it's that rising pitch at the end of a sentence that tells you I'm asking a question rather than just making a statement. It marks salience, letting us emphasize the most important word in a room. It conveys effective meanings, signaling to the listener whether we are bursting with happiness, reeling in surprise, or seething with anger,
all without changing a single vocabulary word. It even manages turn-taking, subtly signaling to the other person when we're done talking so they can jump in.
Let's look at exactly how prosody creates prominence, specifically through what's called lexical stress and pitch accent. Consider this sentence. I'm a little surprised to hear it characterized as happy. Notice how the word surprised just jumps out at you? We call that pitch accent. We are actively choosing to make that word salient. But notice where the accent falls on the word itself. We don't say surprised. Our dictionaries dictate that the lexical stress is on the second syllable. So when our brain decides to emphasize the word, our acoustic hardware automatically makes that second syllable louder, longer, and higher pitched. Surprised. This dynamic texture is precisely what makes human speech so expressive and rich.
Now, what about the syllables we don't stress? Well, our vocal hardware is remarkably efficient, or honestly, maybe just a little bit lazy. It actually takes shortcuts. When syllables are unstressed, we often weaken the vowels into a shorter, lazier sound called a reduced vowel, and the most common of these is the schwa. Think of the word parakeet. You don't pronounce it parakeet with a hard, clear A in the middle. That middle syllable is completely unstressed, so your tongue just relaxes right in the middle of your mouth and outputs this soft, neutral sound, parakeet. This perfectly illustrates how incredibly dynamic our natural speech algorithms are, constantly optimizing energy as we talk.
We've really journeyed today, all the way from ancient Sumerian symbols, right through the intricate physical gymnastics of our tongues, down to the musical intonation of our everyday conversations. The human voice isn't just sound. It is a highly structured, heavily rule-bound code executed by a truly masterful biological machine. So, here is my final thought for you to take away from this explainer. The very next time you speak, will you notice the subconscious processing your physical hardware is doing? Will you actually feel your tongue hit your teeth, your vocal folds vibrate, and your pitch rise to ask a question? I guarantee you'll never think about a simple hello exactly the same way again. Thanks so much for joining me on this deep dive into the code of human speech.